Now, this is a result which I was talking about, that if you have to estimate g theta using maximum likelihood estimator, this result says that you can as well estimate theta hat. You can find the MLE theta hat for theta, then g theta hat would be MLE of g theta. Because note that if you have to find the MLE of g theta, you have to maximize the induced likelihood function. So this theorem says if you have to maximize induced likelihood function, the maximizing parameter would be g theta hat only. So suppose that theta is subset of Rp, let g is a function from theta to lambda, and lambda is an open rectangle in Rq. If theta hat is the MLE of theta, then g theta hat is the MLE of g theta. The proof is very simple. So let theta lambda is collection of all those theta such that S theta is lambda. So let me put here g theta is equal to lambda because I am talking about g. Mx lambda is the induced likelihood function which is supremum theta belonging to lambda Lx theta, lambda belonging to lambda. So I have to maximize this. Clearly this theta lambda forms a partition of theta. Their whole union would be capital theta. So what it means is union over all lambdas of theta lambda has to be theta. Now theta hat is a MLE of theta. This implies that theta hat belongs to theta, which implies that theta hat belongs to theta lambda for some lambda belonging to lambda. Let theta hat belongs to theta lambda hat, where lambda hat belongs to lambda, because I have seen that theta hat has to belong to some theta lambda. So I am saying theta hat suppose belongs to theta lambda hat. Then by the definition of theta lambda hat, H theta hat has to be same as lambda hat. There is some confusion about H and G, you can interchange that. Also since theta hat belongs to theta lambda hat, Lx theta hat would be less than or equal to supremum value of Lx theta, because it is Lx theta at particular value. But this is same as Mx of lambda hat. But Mx of lambda hat would be less than or equal to supremum of Mx lambda. But supremum of lambda Mx lambda is same as supremum over theta belongs to Lx theta, because I know that if you look at the supremum of Mx lambda, which is nothing but actually this quantity would be equal to supremum over lambda, and Mx lambda was supremum over theta lambda of Lx theta. So what you are doing is, and theta lambda forms the partition of theta. So what you are doing is first you are fixing theta lambda, looking at the maximum over there, and then varying lambda. So which is as good as saying that I am taking the maximum of Lx theta over whole theta. So that is what it is over here. But this is same as the maximum likelihood estimate. So everything gets sandwiched because left hand side and right hand side on the inequalities are the same. So that means Mx lambda hat is same as supremum lambda belonging to lambda Mx lambda. So lambda hat, which is S theta hat, is an MLE of H theta. So it says, it's very simple. What it says is if theta hat is an MLE of theta, then g theta hat or H theta hat would be an MLE of H theta. Before going further, let me impose certain regularity conditions. I call those as regularity conditions R1. The parameter space theta is an open interval in R. So I'll assume that theta is an open interval in R. If you minutely see the last result, in last result I have assumed in a very subtle way that my theta hat takes value in the parameter space with probability 1. So that is an assumption in the last theorem which I have not very explicitly written down. Then I assume that my support does not depend on the unknown quantity theta. Then for any x belonging to Sx and theta belonging to x, the derivative del by del theta fx theta exists and is finite. And I know that this whole integral, if you integrate the PDF, that is 1 for every theta belonging to theta. So I am saying here I can differentiate it both the sides. If I differentiate both the sides, I get d by d theta of this quantity is equal to 0. Then I am assuming that I can take this derivative inside. So I am saying that in this expression, I can differentiate under the integral sign so that once I take d by d theta out inside, I get this, which is same as this, which is same as 0, because derivative of 1 is 0. So what I assume is del by del theta of fx x given theta dx is always 0, which is same as del by del theta of fx, integral of fx x given. Now, of course, the same thing I am assuming in the discrete case, except that there this integral would get replaced by the summation sign. Then the second regularity condition, for any x belonging to Sx, the second derivative exists and is finite. Now, this we have already assumed. Then I am assuming that I can differentiate this also under the integral sign. So, this can be differentiated under the integral sign. So, then that means del by del theta of this would also be 0, because derivative of 0 is 0. Then I can take it inside the integral, then it becomes minus infinity to infinity del square by del theta square fx x given theta, which is same as this, which is same as 0, because derivative of 0 is 0. So, these are the regularity conditions which will assume in the sequence. Let me give this remark. Using advanced mathematical arguments, it can be shown that the regularity conditions R1 are satisfied for a large family of distributions, including the exponential family of distributions having associate probability mass functions or probability density functions of the type c theta hx e to power r theta into tx for some functions h, c, r, and t. Now, these are very broad class of families, and you can easily see that this includes Poisson, binomial, gamma, normal, many distributions are covered under this model. Then another set of regularity conditions is, let us look at, for x belonging to Sx, let us look at psi x theta, which is del by del theta log of x theta and the square of that. This would be nothing but, so this is a case where I have theta is real valued. So, it is 1 upon fx x theta del by del theta fx x theta whole square. Now, this represents the relative rate at which the PDF or PMF fx x theta changes at x. The average of this rate is defined by expected value of this quantity, because the rate at which PDF changes, I can denote it by this quantity. So, this, which we call as I theta, represents the rate or the relative rate at which the PDF or the probability mass function changes at the point x with respect to theta. The large value of I theta naught indicates that it is easier to distinguish theta naught from the neighboring values of theta naught, and therefore, more accurately theta can be estimated if true theta is same as theta naught. So, if this I theta naught is large, so that means expected value of this at theta naught is large. That means the PDF is not changing, PDF is changing very rapidly with respect to theta, and if your PDF, your distribution is changing very rapidly, that means your theta can be estimated more accurately, because it would be possible to distinguish thetas, distinguish PDFs for various values of theta. So, in that sense, this quantity I theta is called the Fisher's information of x contained about the parameter theta. Note that I theta is a function of theta belonging to capital theta. Now, let x1, x2, xn be a random sample from a PDF or PMF f dot theta, and let x is same as x1, x2, xn. Then I know that joint PDF is same as product of individual PDFs, each of them is f, so f of xi given theta. Let small I theta and capital I theta respectively denote the Fisher information contained in the single observation, say x1, and the whole sample x1, x2, xn. Then let us look at what is del by I theta, which is actually del by del theta log of x theta. So, log of this quantity, but log of product is same as sum of log, and when you take the derivative, it becomes del by del theta log fxi theta whole square. So, this would have summation, this is same as summation this is square plus summation I not equal to j cross product term, because it is a square of a summation. So it will be summation of squares plus the cross product terms. And that is what we do over here. This is summation of squares and then the cross product terms. Now note that because of independence, the inside quantity, it would become expected value of del by del theta log of f xi given theta, and expected value of del by del theta log of xj theta. But xi and xj have a same distribution, so the cross product term will contribute this. And of course, summation I is equal to 1 to n, summation j is equal to 1 to n. But what is this quantity? This quantity would be 0 because this is same as del by del theta log of x theta, then density of fx k theta, because expectation I am talking about, which is same as del by del theta f prime del by del theta f of x given theta divided by fx theta, which gets cancelled with this dx. And we, because of the regularity condition, we have seen that if I can pass on the derivative sign under the integral sign, then this quantity would be 0. So that is why the cross product terms would be 0, and you get exactly this. But here xi's are IID, so each of these terms would be same when I take the expectation inside. So it would be n times expected value of del by del theta log of fx1 theta whole square, which is nothing but n of I theta. So what it says is, so reasoning I have given, since x1, x2, xn are IID, and expect value of del by del theta log of fx1 theta, which is 0. So what it says is, the information contained in the whole sample, whole random sample x1, x2, xn is n times the information contained in single observations I theta, which is I theta, which makes sense. So that is what we did over here. So let me state this result, which says if x1, x2, xn are IID one-dimensional random variables with common Fisher information given by this, where f dot theta is the common PDF or PMF of the sequence, and let theta be an open interval in R. Let theta n hat be the unique MLE of theta based on x1, x2, xn. So suppose you have a situation where there is a unique MLE. Then under regularity conditions R1, as n goes to infinity, a normalized version of a MLE has a normal distribution with mean 0 and variance as 1 upon I theta. Now certainly if this happens, then I know that theta n hat has to go in probability to theta. So what it says is the MLE would always converge in probability to theta. So that means MLE for large sample sizes is getting very close to the true value of the theta. Not only that, if I normalize it with root n and subtract it from mean, from the actual value of the parameter, I get normal distribution with mean 0 and variance as 1 upon I theta for large sample size.